Hi, my name's Delia, and today I'll be talking about the Giraffa Camelopardalis giraffe population, specifically in a lens of using linear algebra. So let's get started. So just to go over the plan for this presentation, I'll be starting with an introduction of what I'll be studying, the mathematical methods that go into what I'm going to be talking about, and then the analysis of the actual data, and then some conclusions surrounding it. So starting off with the introduction. So the scenario, a team of conservation biologists is researching two populations of organisms, trying to ensure that the populations can sustain themselves for a long period of time without either going extinct or overwhelming the ecosystem. The team has hired me as a mathematical analyst to model the populations and make recommendations about how to stabilize their growth. I will be providing realistic solutions to the issues facing my chosen population, which, as I said earlier, is the giraffe. And the specific giraffe we'll be talking about is the Nubian giraffe, but I'm just going to call it the giraffe for the rest of the presentation just to save time. The estimated number of Nubian giraffes around the world is 3,000. The majority of them live outside their natural range of habitat as a result of efforts to establish viable populations across Kenya for conservation purposes. There's very little information about their presence in Ethiopia and South Sudan due to increased poaching. The rate of decline in the past 3.5 decades is around 95%, and they're on the IUCN Red List as critically endangered, indicating an urgent need for further conservation efforts. So to get into some more of the specific threats that these giraffes are facing that contributed to that 95% decline in population, the main issue is the loss of their habitat. Giraffes used to roam across the African savanna. However, as I said earlier, they now live in small communities across the continent. Habitat loss has mainly been caused by the conversion of woodlands to farms and ranches. Additionally, the charcoal industry has many jobs involving harvesting trees and burning wood to make the charcoal, and climate change and droughts have also played a significant role. Giraffes rely on these trees for food, driving them out of these areas. So without the trees, they have no food. Development and increasing human populations in these regions has resulted in giraffes becoming hit by cars as well. Civil wars have contributed by increasing wildlife trafficking and poaching as people face pressures on their livelihood and loss of jobs. The international market has only incentivized this poaching, with giraffe products being listed online. And disease also plays a role with the intermixing of giraffe species due to the loss of habitat, including diseases like lesion-inducing skin disease. So overall, there's a lot of threats they are facing, and a lot of different factors that have gone into their decline. So on to the fun stuff, the data. So the specific populations that I'll be analyzing for today are the first one on our left, matrix K, which is data from the Giraffa, hopefully I'm saying that right, from 2008 to 2010, and Serenera from 2008 to 2010, and I'm going to call the one on the right matrix S for Serenera, matrix K for Giraffa. Pretty straightforward. The data is modeled using stage-structured transition matrices, which I'll get into exactly what they are in a few slides. The main question guiding this investigation are what are some specific actions that can be taken to bring the giraffe population back to a sustainable level, and how do the two different geographical areas compare into overall giraffe sustainability? So in case you're like me and you're like, where in the world are we even talking about, Delia? Like, I've never heard of Serenera or Giraffa before. Well, neither have I. So basically, we're talking about Africa, specifically Tanzania, and then the top of Tanzania we have, oh, I just realized the pointer's not on. Let me turn that on. Right here. So we top of Tanzania, right here. Okay, moving on. So on to our mathematical methods. So population vectors and transition matrices can easily be explained through an example of the butterfly life cycle. Population vectors provide an organization for the number of organisms in each type of stage or groups of ages. On the screen, this vector p of x is right here. And it shows that there are 100 eggs, 500 larvae, 400 pupae, and 200 adults. This organization makes it easy to find the total population, subsets of the population, and each life stage total very easily as they're listed in order of life cycle. Populations often change over time due to certain life stages being eaten or dying for some reason, and this is where transition matrices come into play. Transition matrices allow these changes to be modeled over time to see how the population of each life stage changes. These changes observed in the wild can be mapped to linear equations, which then can be modeled into a matrix. On the screen, down here, there's an example of a set of linear equations for the butterfly example created by Johns Hopkins CTY. The transition matrices take the coefficients from these equations to create L P of t equals P of t plus 1, where PT is the population vector described at the beginning at time t. This put together can create the matrix seen right here that I made. And T of x is broken down into eggs, caterpillar, pupae, and adults, kind of in that order. So you have eggs, and then right here. So starting in the second row, so we're at the 0.5 here. This means that 0.5 of the eggs become caterpillars, and then moving to the 3/4, that means that 3/4 of the caterpillars pupate, and then moving down again, half the pupae becomes adults. The 0.2 stays in the adult row column because these are the adults that survive. And as you can see, the row indicates the starting stage like an egg, and the column indicates what it becomes like a caterpillar in this example of the 0.5. Where it becomes complicated is kind of in this first row here, because the adults contribute to the eggs. So we're in the egg row in the adult column. Each adult lays 30 eggs, but only 0.2 are surviving. So multiplying these two numbers together, you get 6. So that's why the 6 is in that position. So transition matrices and population vectors can be broken down by stages of life, where the butterfly or like with the butterfly or ages. For the example, the first category could be like 0 to 2, and the next one could be 2 to 4 years. These are called stage-structured matrix models and age-structured matrix models. So like stage-structured is like egg, larvae, like words, and age-structured obviously is just like 0 to 2, 2 to 4. To model the future using transition matrices, one simply just needs to multiply the transition matrix by the population vector to get a new population vector. So just a quick example, I did this with Symbolab to show what the butterfly population would look like in a year. So basically you just take your transition matrix and multiply it by the population vector, and then you get the new p prime of x. So to do more years in the future, you're just going to raise the transition matrix to the correlating power. So if I wanted to do 3 years, I would raise transition matrix to the 3rd power, then multiply by the population vector to get that. So transition matrices model the future very well, and the past not so well. Past is pretty much the same process, except you're doing negative powers. So if I wanted to do 3 years in the past, I'd raise the transition matrix to the negative 3rd power, and then multiply it by the population vector. So pretty straightforward, except like obviously you need to take the inverse and then raise it to the 3rd power. So that is an extra added step. But it's not that great at modeling things in the past, as we saw with the COD presentation. It's a little wild, but it certainly can be used to predict the past if you would like to take that method. All right. So, are transition matrices always invertible? A very good question. So, yes. And you're like, why does this even matter? Well, like I was saying before, if we want to predict the past, we have to take the inverse of the transition matrix. So it's kind of important if they're always invertible. So yes, they are always invertible. Without delving too deeply into the proof, which you can read for yourself right on the screen, transition matrices are invertible because they never map any non-zero vector to a zero vector. This means they always have full rank, ensuring that their columns or rows are linearly independent. And if you want to read some more specifics of the proof, they're right here. So, long-term growth rate. So G is the long-term growth rate and is given by the limit as the time frame approaches infinity of n of t plus 1 over n of t. To estimate this, we simply need to calculate the number of giraffes in the future for a reasonably large time away and one step below that. I picked 20 years in the future in 19 years because that was the highest number that Symbolab would let me pick. And you don't want to do these calculations by hand because raising a matrix to the 20th power is an insane amount of matrix algebra you're going to be doing, and that's just like not reasonable to be doing out by hand. I ran these calculations with matrix K representing the giraffes from Kirawira. I made up a fake initial population vector labeled as S0. The initial population vector doesn't matter since we're looking at the proportion between numbers and not the exact total. I raised K to both the 19th and 20th power and multiplied by S0 to obtain two new population vectors, S of 20 and S19. Since one cannot divide entire matrices, I divided each individual entry in S20 by the respective one in S19. For example, the purple entry got divided by the other purple entry. This division resulted in G, as seen, where are we? Right here. And the G is the same for every entry because it's just the same proportion of S20 divided by S19. So pretty straightforward. You can see all the math right here on estimation of G. You got K, this, and then we're multiplying our vectors, and then just purple divided by purple. I should have a little example right here. So we take that, plus this one and divide by this one, and then we get right here. And they're all the same. So this 1.02 is our estimation of G. In terms of computing G exactly, we have that over here. One simply needs to find the largest eigenvalue of the matrix. In this case, we had right here this about one-ish number, and then like to get that eigenvalue, we obviously had to take K, subtract I times the lambda, and then get the characteristic equation, then solve that, and then find that largest eigenvalue. So you're like, why does that number look so familiar? Well, it's because it's basically the exact same number we had here, showing how good our estimation was at actually finding G. So the value of G for the stability of the population means that if it's greater than 1, the population is increasing exponentially. If it equals 1, the population is staying the same, and if it's less than 1, the population is decreasing. G is related to the eigenvalues by being the largest eigenvalue of the transition matrix. This eigenvalue indicates the dominant trend in the population dynamics. The determinant of the transition matrix is the product of its eigenvalues. For a stable population, the determinant should reflect the balance of growth and decline rates. The rank of the transition matrix is the number of linearly independent rows or columns. For the matrix to describe a meaningful transition system, it should have full rank equal to the number of states. A rank deficient matrix implies redundancy or dependency among states, affecting the accuracy of G. All right, so to estimate the long-term proportions of different life stages in a population model, such as seedlings to adults, you can use the concept of a steady-state vector. This is done by first finding the positive eigenvalue with an all-positive eigenvector. I did the calculations with matrix K because we had already found lambda on the previous slide. To find the eigenvector, one subtracts I times lambda from K, row reduces and solves, so here's me doing that. And lambda is not just like me using that as like a variable. Lambda is like the actual lambda, the 1.029, I think it was, from the previous slide. And yes, so here I wrote 1.03 to quickly round that, just so I didn't have to write it all out. So then we have our eigenvector after we row reduce, and then we need our, since this is like a proportion of a population, so the whole proportion would be 1. So we need everything to sum to 1 to be a proportion of an entire population. So we have to add up all the entries and then divide by that total to get a proportion. And then we finally get our steady state vector. So this vector is independent these proportions are independent of the actual like initial population vector you're feeding into it. So yes, the final population, steady state population, does depend on the initial population vector you multiply this by, but it does not affect the proportion. These are going to be the set proportions of the long-term distribution because the population vector, like initial, has nothing to do with the process we just did. We're working with the transition matrix. So if you were to change the transition matrix, yes, the like final proportions would be changed, but that initial population vector you could have, it doesn't really matter. It's only going to affect the actual like amount of each species per category. It's not going to affect the distribution and proportion of them. So just to kind of give a number example, like if in this first entry, this is like about 18% here. If our initial population for that first life stage was like 100, then like the long-term population would be 18 for that that first example. But like if our initial population was like 1,000, we'd actually have 180 of that first life stage. So that's like how it affects the population, big population, but not the distribution. So it's always going to be 18%. So the distribution is not changing. Population proportional vectors. A population vector V is called population proportional if under transformation by a transition matrix A, the components of V remain in the same proportion. This means that AV equals lambda V, as you can see here on the screen, for some scalar lambda, which is that. In other words, V is an eigenvector of A with eigenvalue lambda. So the set S is defined as a set of all linear combinations of these population proportional vectors. Since these vectors are eigenvectors of A, S is the span of the eigenvectors of A. So you may be wondering, is S a subspace? Yes, S is a subspace. This is because the zero vector is trivially a linear combination of eigenvectors by taking all coefficients as 0. The sum of any two linear combinations of eigenvectors is also a linear combination of eigenvectors. And 3, any scalar multiple of a linear combination of eigenvectors is also a linear combination of eigenvectors. Therefore, S satisfies all of the conditions for being a subspace. So you also may be wondering, how does the transition matrix affect S? The transition matrix A acts on S by scaling vectors in S by their corresponding eigenvalues. Specifically, if V is an eigenvector with eigenvalue lambda, then AV equals lambda V. This means that A preserves the subspace S and acts diagonally in a basis consisting of eigenvectors. Dimensions of S. The dimensions of S is the number of linear independent eigenvectors of A. This is the number of distinct eigenvalues of A. If each eigenvalue has geometric multiplicity equal to its algebraic multiplicity. In general, the dimension of S is the dimension of the eigenspace corresponding to the set of all eigenvalues of A. A 4x4 transition matrix with two qualitatively different kinds of population proportional populations. So if we wanted to make an example of that, A should have two distinct eigenvalues. For example, matrix A right here has two distinct eigenvalues, 2 and 3. The eigenspace for eigenvalue 2 corresponds to populations proportional to the first two components, and the eigenspace for eigen 3 corresponds to population proportional to the last two components. To have only one kind of population proportional population, B, we're on B. B should have a single eigenvalue. For example, here in matrix B, it has one singular eigenvalue, 2. Thus, any population proportional vector is just a scalar multiple of the vector 1, 1, 1. All right, linear transformations and rank. If we understand the transition matrix as representing a linear transformation, it transforms the space of population age distributions. Each column of the transition matrix represents the age distribution of the population at a certain time, for example, the year, while each row represents the age distribution of the population in the subsequent time period after one transition step. The significance of the rank of the transition matrix in terms of understanding population structure and long-term population dynamics lies in its ability to capture the dimensionality of the population space. The rank of the transition matrix indicates the maximum number of linearly independent columns or rows in the matrix, which corresponds to the number of distinct age classes or stages in the population. For example, if the rank is equal to the number of age classes in the population, it implies that each age class contributes independently to the population dynamics. If the rank is less than the number of age classes, it suggests that some age classes are dependent on others due to like a shared demographic process or constraints. Transition matrix with full rank equal to the number of age classes indicates a stable population structure where each age class contributes uniquely to the population growth or decline. In contrast, a transition matrix with reduced rank may indicate dependencies or feedback loops within the population structure, potentially leading to a less predictable long-term dynamics. In addition, the rank of the matrix can make it more sensitive to change. Higher rank matrices often exhibit greater resilience to slight changes, as changes in one class are less likely to affect the entire population structure. Lower rank matrices, on the other hand, may be more sensitive to changes, leading to amplified effects on population dynamics. So a sensitivity analysis reveals the extent to which a population's long-term growth rate relies on the various entries of the transition matrix. This sensitivity can be approximately computed as delta G over delta A, where delta G denotes the change in the growth rate when a matrix entry A is altered by a small amount while keeping the other entries fixed. To illustrate this process, I conducted a sensitivity analysis on the matrix derived from my first project concerning sustainable codfish populations, denoted as matrix L prime prime. Specifically, I examined the alteration of the second entry in row 1, which is right here. Let me circle it. It's right here in the reddish orange. L represents the original cod transition matrix. I modified L prime prime to only adjust the highlighted entry in red. So this red thing right here. To also keep the other entries fixed. So I made L prime prime prime, which is right here, and you can see that it's basically the same as L, except I kept that highlighted change and I have the 1.2 here. So the initial step involved determining the change in A, represented by the highlighted entry. In L, it is 1 versus in L prime prime prime, it is 1.2, so that results in a change of 0.2. Next, I proceeded with calculating the eigenvalues for both L and L prime prime prime, and that's because we want to find G, which we know from previous slides is the eigenvalue. Okay, so to do that, obviously I had to do each of the matrices subtracted by lambda, I times lambda, and then find that characteristic equation, then solve for that biggest eigenvalue. So we have those two right here, and then I had to subtract the two eigenvalues, and then do the, so the eigenvalues, like I said, is delta G, or sorry, is G, and then to find delta G, you have to subtract the 2, and then we put that over the delta A, which I said earlier is 0.2, and then divided, and then we got this number, this 0.2, about 4-ish number here, and that was our sensitivity analysis. Now on to a deep dive analysis into the giraffe population. So proportions, based on the math from the long-term distribution slide that used eigenvalues to compute the steady state vector for matrix K, we expect the proportions shown on the left. So this is just the math that I explained earlier regarding matrix K and finding that distribution. And then doing out the math, the same process for matrix S by taking the eigenvalue provided by Camelopardalis. So instead of actually doing the eigenvalue computation by hand, luckily they provide it online. So I just quickly went through and took that to find the eigenvector and then normalizing it to get the steady state vector. And that way we have our two distributions of the population. The proportions are very similar. This makes sense considering the original matrices were also very similar in terms of values. We see a slight increase in the percentage of adults in calves in matrix S over here, and an increase of subadults in matrix K steady state vector here. These are the expected proportions because the steady state vector finds where the populations level out, achieving a balance. As stated earlier, the initial population vector is important in determining the number of giraffes, like in the long run, like the specific number of them, because you're directly multiplying the initial vector for each of the three groups by the steady state vector. And like I said earlier, like this is like about 18%. And depending on if you have like 100 or 1,000 initial giraffes, that is going to change when you multiply by that percentage, the final kind of steady state population. For proportions, the initial population vector isn't important because it's not used in the calculations, like I said earlier. Only the transition matrix is used. So these are the proportions no matter what the initial population vector for the giraffes are. So, altering life stages. Which life stage transitions have the biggest impact when altered? A very good question. With matrix K representing a better matrix scenario with the endangered giraffe population increasing, so matrix K is here, and versus matrix S with them decreasing, and we know that based on the eigenvalues, this one's greater than 1, this is less than 1. Finding out kind of where matrix S goes wrong and why it doesn't have a eigenvalue above 1 is kind of very important when we're talking about like a dying endangered species. So there's really 4 entries that we need to compare, all of which are highlighted because the rest are the same with zeros. So we're going to... Okay, so we can see the math for the 4 different entries above over here. So we got our 4. As in the mathematical methods section with the COD, we find delta G by dividing delta G by delta lambda for the 2 matrices. In each case, matrix S is changed to only have 1 different entry from matrix K to compare 1 entry at a time. The eigenvalues then found input into the equation, like by subtracting the 2 and then doing delta G divided by delta A. Based on these calculations, the life stages we should be most concerned about are right here, the birth rate from the adults, and then also the survival of calf to subadult, with these having kind of the highest effect. Yes. So there's that one, and there's that one. We got our arrows. So kind of just to give a visualization of how matrix S is like not really a good scenario, and how even matrix K isn't like the best. I just put in a random initial population vector that I believe it was the initial was going down from the calf to adult was 100, 200, 300, just to give some random numbers in. And this is kind of what it looked like. So we can see here like how bad matrix S looks compared to matrix K. So we really want to work on increasing matrix S because it's like literally just like heading down, 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 down. And this is only after 15 years, so not great. So with an endangered population, obviously we don't want the matrix S scenario. So in terms of conservation efforts, as stated prior, it's essential to work on raising the survival rate from calf to subadult and the overall birth rate. The good news is that based on my research, the youth not surviving to adulthood isn't primarily due to climate change, habitat loss, or disease. It's mainly due to natural predators. In a normal, stable population that wasn't severely endangered as the giraffes, this predator relationship would be okay. However, with the giraffe population dwindling, it's essential to prevent so many predators from eating the giraffes. It's important to keep in mind that with fewer adult giraffes due to factors like poaching, climate change, and habitat loss, the youth are more susceptible to predators and cannot be protected. Male giraffes leave their mothers at around 18 months, and females stay in the herd as their mothers. Possible efforts could involve placing like harsher punishments on poachers for hunting like the adult giraffes. So like that would be bad because like then the calves are no longer with a mother and can be protected. More conservation type focuses could include enhancing monitoring and surveillance, increasing the number of patrols and monitoring in areas where like calves are known to be at high risk from predators. Using drones and cameras can help trap and track predator movement and giraffe interactions. Safe zones could also be created, which are predator-free zones with areas where like the calves can grow up and thrive without the threat of being eaten. And this can involve active management of predator populations or physical barriers to keep predators out. And then thirdly, community involvement, engaging the local community in anti-predator efforts by training them to identify and report predator sightings and help them understand the importance of giraffe conservation. In terms of the birth rate being so low, this is mainly because the giraffes are like so segregated in different communities, like conservation areas, which would only be like further emphasized with these conservation like areas that I was proposing without like predators. However, by increasing the amount of calves that are surviving to adulthood, you're also increasing the number that like can have babies again. So by just keeping the young to survive longer, you're going to be able to increase the birth rate by having just more giraffes around. And that's kind of the main way you increase the birth rates, by just having more giraffes. So in terms of what we want the giraffe population to look like in the future, population stability should not be the goal. Instead, growth is needed. The population in general is extremely low and is at extreme risk of extinction. Exponential growth of the giraffes would be beneficial, as both matrix K and S should take these actions, because just having a growth rate a little above 1 is not great. They're so close to being extinct, like that it needs to be a lot bigger than just barely over 1. And also like you need to create room in case something bad happens in the growth rate. So basically we'd like to see both of these groups start growing exponentially a lot more. And we don't really need to worry about overpopulation of the giraffes just because they're so critically endangered now, and there's only like 3,000 of them left. Just getting them up and then stabilizing the population would be the best choice of action. All right, on to the conclusion. So to summarize, we really want to focus on getting the number of calves to the subadult life stage to increase. And by doing that, we're also going to then have more adults, which means the birth rate is going to increase as well. And with that, we want to make sure we're implementing conservation areas so that predators are not eating the calves, and kind of getting community involvement and more just monitoring. And that could involve, like I said, like having more stricter punishments for people that are like poaching. And we also need to still be aware of other issues that the giraffes are facing, like climate change and habitat loss, all those important things. We did a analysis on the groups and did all that math out and found all this data. And our original matrices are here for reference. And we want to see the giraffe populations grow exponentially, not stable out, just to ensure that they're not critically endangered anymore. So obviously we can't conclude a presentation without acknowledging kind of some of the outside phenomena that the matrix model doesn't acknowledge. And the model assumes a consistent survival and birth rate over time, which are unrealistic in a changing world affected by environmental variability, predator-prey interactions, poaching pressure, habitat degradation, and climate change, which are all constantly changing and in flux. Another major oversight is the assumption that every giraffe is capable of reproducing, ignoring the fact that like male giraffes cannot have calves. And these factors challenge the conclusion that all models will eventually reach a steady state. And birth and death rates will fluctuate over time due to various factors, leading to fluctuations in the giraffe population from year to year. These dynamic factors make it impossible to create an accurate model using this matrix approach because of the underlying rates crucial to the model that will continually change. And obviously representing half the population incorrectly, the males, makes the population appear larger than it actually is, as the males cannot contribute to reproduction but can die, and which kind of distorts that overall like population and is not going to be completely accurate to the real world. So the usefulness of this model is very similar to in the situation of the cod population video, and it's very heavily reliant on computing power just to do like the estimation of delta G. We had to use like raising a matrix to the 20th power, which is definitely something you're not doing by hand. So it requires, and also just looking at our data, we had long decimals of answers. So it's very heavily reliant on computing power. And over like many years of like predicting data, you're going to have more multiplying the matrices. And at a certain point, it becomes tedious and nearly impossible. So especially in like scenarios where populations are not going to reach a steady state. So computers are essential to complete these calculations for many years in the future and do those really hard matrix multiplication. And even just Symbolab wouldn't go past 20 years to do like predicting into the future. So that's like obviously raising the matrix to the 20th power. So having computers that are capable to go beyond that is going to be important when you want to do like 100 years into the future. So very important and very cumbersome to do by hand. And also when we're talking about like the rank of a matrix and just like how many columns and rows it has, the more you have, the more tedious the multiplication becomes. So computers enable the calculations to be more precise by allowing you to have more breakdown between like the years, like if you want to have a 0 to 2, 2 to 4, like, and be able to do that for longer time instead of just like the matrices I had only had a rank of 3 and 3 columns and rows. So being able to do that with larger matrices is another great benefit that the computers have, and they can obviously do it to a more precise level with decimals. And I learned to have a really good appreciation for the computers during this project because it is a lot of work to solve these problems out by hand, and I don't want to be solving like a matrix raised to the 20th power. So it's great that computers can do this, and hopefully we'll be able to improve this for the future, and Symbolab will be able to do something above the 20th power to get more accurate results. So on a large scale, the model can be used as a part of many solutions to our global problems, many of them listed here. For example, like population growth and demographic analysis. The model can help like in showing the age distributions of like communities in Japan that have like an excessive number of elder people. And it also can be used to like predict the future of a country's age distribution and help understand birth rates, death rates, and help with overpopulation. And then, like in the case with the giraffes, it can help with conservation biology and like hunger, and like we can monitor endangered species affected by climate change, or even like populations of invasives and kind of keep them under control. and also help kind of with resource management like we did with the giraffes, and target specific areas that could be improved, like the subadults or the adults, and kind of find the issues that are relative to those groups, whether it be like hunger or like their source of water, things like that, and be able to take more targeted approaches that will eventually save us money and like get the most for what we're investing to save these species. And then disease modeling. The model can be used to show the death and reproduction rates of people affected by certain diseases. It can show the effect of people across different age groups and kind of what the population would look like after, like the infected population could look like. And then, like we said earlier, the oversights of these models to the unpredictability of real life in our changing world could cause the model to exacerbate problems or minimize them. And while, yes, they could provide a strong guideline to help follow with problems like overfishing, the giraffe population, and like other wildlife conservation issues, these guidelines could easily be wrong or change very quickly in our world. Following these guidelines exactly could lead to like things like overfishing or like not enough species being protected, like the giraffes. And this kind of applies to all the situations that I kind of went through, that following the guidelines directly to the bone, like for like overfishing, like if you're fishing the exact amount you need, like the fish population could change really quickly, and like people there, fish could die because like of a oil spill or something. Like the world is very unpredictable, so following guidelines to keep a population stable to the T can result in actually being harmed in the long run. And so it's kind of very important to use many different types of models in these situations, and to kind of double check the provided guidelines to take into account many different factors and provide the best overall advice. So kind of to conclude this giraffe presentation, I learned a lot about linear algebra's applications using specific real-world data, and also learned a ton about the giraffe population and what we can do to help, and the benefits and disadvantages of using the transition matrix model. Nonetheless, with cautious consideration and using other mathematical models to kind of supplement, the transition matrix model can contribute significantly to solutions for these pressing issues, like in the giraffe example. So thank you. Hopefully you learned something about the giraffe population, and hopefully we'll start taking some more steps to help them stop being critically endangered. So that's it. Bye.